Hello, I'm A Hilmy, a final year software engineering undergraduate. In this video, I'll be presenting my final year research project titled Comparative Weakness Identifier. In this video, we'll be discussing the following. First, let's look at the problem background. Let's first try to understand the problem. I'll be explaining this with a diagram. Hopefully, it'll be easy to understand. We all know, and it is nothing new, that with the advancement of technologies, establishing and growing new businesses is easier than in the past, especially in the tech industry. In addition, with the growth of these businesses, new products are launched every day. Regardless, that is, if it's a new or well-established business, all of them are always working towards one goal, which is how to grab the attention of customers towards their products. There starts a competition between two competitors who offer similar products. Competition here is the battle for customers. From a consumer's point of view, these competitive products are alternatives. If in case your rival offers a better product, consumers, including your regular consumers, may get attracted towards your rival's product. Due to this, it is highly important or much necessary that businesses are always aware of what consumers think of their product, that is, their opinion on their products, the good and the bad, and what their competitors are doing in order to secure higher rank in the market. In the business world, they are known as consumer intelligence and competitor intelligence. Businesses are always looking for opportunities to grow their business. They may make use of these techniques to identify the exact needs of their customers and what customers expect from them, so that they can secure a higher rank in the market. And it doesn't stop there. The cycle repeats. To summarize all what I said, market is flooded with similar products day by day with the growth of organizations in the industry. Here we discuss two stakeholders. They are the consumers and competitors. Organizations have to be aware of all expectations of the customer and the movements of their competitors so they can win the market. Next, we'll be looking at the proposed solution, and I'll be explaining this with the help of a concept map and an architecture diagram. Our solution to the above problem can be solved within the opinion analysis field in NLP. Therefore, I'll be explaining all choices we made in order to come up with our solution, which is based on existing literature. Opinion analysis can be done at different levels. Since we are focusing on predicting a comparative opinion of a product, we have chosen to do it at sentence level. Through this research, we will also be focusing on the aspect extraction area using a novel technique. When it comes to the languages that have been explored through opinion analysis so far, the most popular one has been pure languages, which means text in a single language. With the introduction of Web 2.0, accessing different sources of data has been much easier. Therefore, we have chosen to analyze the opinions of customer reviews that have been publicly available. Prior work in opinion analysis have been conducted using machine learning and lexicon-based approaches. Here, we choose deep learning as traditional machine learning techniques have already been exploited. Next, opinions are of different kinds. We specifically chose comparative opinions for this work because we intend to compare two entities, and that can be done using comparative opinions. Existing work shows that all machine learning techniques have been explored. To the best of our knowledge, there had not been a neural network model introduced for comparative opinion mining tasks. Therefore, we decided to experiment with a CNN model without going for complex models. For evaluations, we will be using the most popular evaluation measures used in binary classification research projects. So, we go ahead with confusion metrics and their measures and the two curves ROC and precision recall. Next, we will discuss the high-level architecture. Here we will be using a three-tier architecture where the presentation layer houses the user interface, logic layer is responsible for the logical processing of the input to output, and data layer housing the developed model and data. In the next slide, I will show the UI frameworks of the proposed solution. The presentation layer has four interfaces, from the home page to the input collection page to the final analysis output. This is how the wireframes look like. In the logic layer, first the input will be passed through the data preprocessing pipeline to prepare the data for analysis. Then it will be passed into the weakness identifier, where the comparative opinion is predicted out of a given comparative sentence and then passed into an algorithm that extracts the comparative keyword. Finally, it analyzes the outputs of the two previous pipelines to determine if a particular product is positive or negative when compared with its competitor, and determine the compared aspect. The data layer will consist all the data used here and the developed models for this work. Next, we will look at a demonstration of the proposed solution. First, I'll take you through the comparative sentiment prediction pipeline. First, let's download all data necessary for the training process. Then we import all the required libraries. Here we read the dataset into a data frame and assign each column into a variable. In this section we'll be tokenizing the words. For this we give the padding type as post and max text length as 100. Then we tokenize the text by padding the sequences with these values. Then we create a vocabulary size. Here we create the embedding index out of globe embedding. We use globe 6B with 100 dimensions here. Then we create an embedding matrix for our corpus. Next we'll look at our model. Here we developed a sequential model and added multiple layers on top of it. First we pass an embedding layer by giving the vocabulary size, embedding dimension, and our embedding matrix. The parameters here are not trainable. Next we add a dropout layer with a dropout rate of 0.2. Then we add a one-dimensional convolution layer with 250 filters, 5 as the kernel size, and ELU as the activation function. Then we add a max pooling operation for 1D data. Then again we add a one-dimensional convolution layer with 250 filters, but here we reduce the kernel size into 3 and we give the same activation function ELU. Next we added a global max pooling 1D layer and then a dense layer with 250 units and the same activation function. Finally, again we give a dropout layer with a dropout rate of 0.2. The last layer is a dense layer with 1 unit, 1 neuron. The activation function used here is sigmoid because we intend to predict a binary value. This is the summary of the model. Then we split the dataset into train and val sets by giving a test size of 0.3. Here we prepare 3 callbacks, one for TensorBoard to save the logs, and here we use model checkpoint and early stopping to avoid overtraining of the model. In our model, we are using the Adam optimizer with a learning rate of 10 to the power of minus 6. We compile the model by passing binary cross entropy as the loss function, and we provide accuracy as the matrix. Training is done with a batch size of 32 and 200 epochs. Then we train the function by passing the x train values, y train values, the above batch size, above number of epochs. Shuffle is given as true so that data is always shuffled for each epoch. And we provide the validation data in order to measure the accuracy. And then we pass the 3 callbacks we prepared before. Let's start training. This might take some time. In this notebook, we will look at the aspect extraction pipeline. Here we will be using 2 keyword extraction libraries. One is Yake and the second is KeyBird. Yake uses a statistical approach. Therefore, the keywords extracted using Yake preserves the order of keywords from text. In contrast, KeyBird generates keywords, therefore it does not preserve the order of keywords. However, in our approach, we will be combining results of both and calculate the similarity of both sets of keywords generated from both the libraries. For this, we will be using rogue score and species similarity score. Our final similarity score will be a combination of rogue and species similarity scores. So let us first import the keyword extraction libraries. For KeyBird, we will be using this base model from SentenceBird. Then we will be creating keyword extraction and keyword generation functions. For Yake, we will be returning the top 10 results or top 10 keywords as extracted by Yake. Then we create a function to extract keywords from keyword by providing an upper bound and passing the sentence. The keyword model will extract keywords from a given sentence, and we provide an n-gram range which is between 1 and the upper bound. Here too we will be returning the top 10 results as generated by keyword. Then we will be importing the similarity measures we will be using in order to calculate the similarity score. Here we will be using rogue 1 and rogue L, also the similarity score from spaCy. Let us import these. Then we create our function to extract aspects and calculate the combined similarity score in order to generate the keyword that has the maximum similarity score as the comparative aspect. Here the combined similarity score is calculated by getting the F measures of rogue 1, rogue L, and measuring the similarity between each keyword generated by RK with each keyword generated by keyword, and the combination of these three similarities will give us the final similarity score, which will then be used to calculate the total similarity score, and then the keyword which has the maximum similarity score will be returned as the keyword or the aspect. This function takes the sentence as a parameter and passes the sentence into the Yake keyword extractor. This will extract the top 10 keywords as per the algorithm. Then we create a dictionary to store the similarity score data. We iterate the keywords extracted by Yake while generating keywords from keyword. The parameters given into the custom function we created above is the upper bound and the sentence that should be used to generate keywords. We provide the upper bound as 2 so that the maximum number of n-grams or words that could be present in an aspect can be 2. In this nested for loop, we iterate the keywords extracted by Yake and the keywords generated by keyword. We calculate the similarity scores between the keywords extracted from Yake and the keyword generated from keyword using rogue scorer, and then get the F measure of rogue 1, which is for 1 n-gram, the F measure of rogue L, which is for longer text, the similarity between the two keywords using spaCy. The product of all three values will be considered as the similarity score, thereby the total similarity score will be calculated. The similarity score data dictionary will store all the similarity scores, will store all the total similarity scores, and the keyword with the maximum similarity score will be returned. We will look at evaluations and future work. Evaluations of this work was done in 2 stages. First, we'll look at how we evaluated the models. We used different evaluation metrics that were used in existing literature. All evaluations were conducted on a held-out dataset. First, we calculated the confusion matrix. We were able to obtain an accuracy of 92.19%, which is a little higher than the benchmark. We calculated the precision to be 80.74%, recall to be 82.8% and F1 score to be 81.76%. Then we printed the classification report for the test data. This shows the precision, recall and F1 scores for each of the labels. The distribution of data among the classes are not equal, and this shows that the occurrence of a comparative review that has a natural tendency of having the positive entity towards the beginning of a comparative sentence is high. We also plotted the ROC curve and the precision recall curve. The ROC and PR curves are seen to be having acceptable shapes for a good classifier. Area under the ROC curve was 0.962 and the area under the precision recall curve, which is the average precision score, is 0.894. Next we will look at some of the expert evaluations. This is what experts had to say. Most of the evaluators belong to the industry and are currently working in the field of NLP. They mentioned that the research is unique in all aspects and has much scope in the NLP area in the future. Overall, they identified a uniqueness in every step of the research, including data augmentation and using state-of-the-art models for aspect extraction. They appreciated the research in terms of the uniqueness of the research topic and the application of modern technologies to develop an end-to-end solution. In addition, it was mentioned that the researcher has done a deep research for a bachelor thesis. Some mentioned that this unique concept can be applied in many domains, not restricting to the domain of the dataset that was used for training. More evaluators mentioned that the scope is too broad for a bachelor's. Also, they appreciated the deepness of the research and the time spent by the researcher while suggesting future directions. Next, we will look into the suggested future work based on our work. We have identified 3 areas of improvement. For comparative text-related enhancements, it is necessary to have a method to split a sentence into phrases such that each phrase describes a comparable entity. Also, an algorithm to extract a single common aspect from complex sentences is required. In terms of the dataset, we need a technique to mine reviews with aspect information using few words. Also, since there is no standard dataset used in comparative opinion mining work, it is necessary to build a standard benchmark dataset. Next, in terms of the model, further experiments can be done using pre-trained models to predict comparative opinions.